In this video we are going to solve problem 5.6. First you can try to solve this problem. If you are unable to solve, then you can see the full video. This problem has two parts. In part A, the problem is as follows. A phonograph record carries a uniform density of static electricity sigma. If it rotates at angular velocity omega, what is the surface current density K at a distance s from the center? So first we will see what is phonograph record. So this figure is a phonograph record. So basically it is a audio recorder that stores the audio, then plays the audio. So we can say it is a recorder and player as well. So it is used for the reproduction of music throughout the 20th century. In phonograph record, there is a disc that rotates. So we have to find the current density if there is a sigma surface charge density and it is rotating with angular velocity omega. So let's make that disc like this, and we have to find the surface current density at a distance s from the center. So we know the basic definition of surface current density is K is equal to di upon dl perpendicular. Let's consider an infinitesimal element area, that is this infinitesimal element area. Let's say these elements have a charge dq. How we will find this charge dq? So if at a particular time, let's say it is an infinitesimal time dt, it moves a distance dl, because let's suppose omega is anti-clockwise. So if it moves a distance dl, then we can say that dl and the perpendicular distance, that is ds, because we are considering infinitesimal element area. dq will be dl and ds sigma. Let's suppose it is having a velocity v at that particular moment. So dq is equal to v dt ds sigma. di will be dq upon dt, that is sigma ds and v. In this case, what is the dl perpendicular? So you can see the charge is moving in this direction. So dl perpendicular will be ds. So dl perpendicular is ds. When we find k vector, then it is sigma v vector. So we can write the surface current density in terms of surface charge density and its velocity. And we know that v vector is equal to omega vector cross s vector. In case of a disc, we will assume a cylindrical coordinate system. So cylindrical system is like this: x cap, y cap, z cap, and this is our disc. So at a particular point, that is s, and that is, let's increase it, that is phi, and that is z. It is rotating with the angular velocity omega. Let's suppose it is rotating about z axis, that is omega. So we can write the omega in vector form using right hand thumb rule, that is omega vector is equal to omega z cap. So s vector will be as s cap. So s cap is this direction. So when we find v vector is equal to omega vector is omega z cap cross s cap. So v vector is equal to omega s z cap cross s cap. Now we have to find z cap cross s cap. In cylindrical coordinate system, we can relate it with a Cartesian coordinate system by remembering this matrix. So this matrix is as follows, that is having s cap, phi cap and z cap is equal to cos phi sin phi 0 minus sin phi cos phi 0 0 0 1 x cap y cap z cap. So we can easily relate the unit vectors of cylindrical coordinate system and unit vector of Cartesian coordinate system using this matrix. If we want to find out z cap cross s cap, then z cap cross s cap is z cross cos phi x cap plus sin phi y cap. After solving, it will be cos phi y cap minus k sin phi x cap. From this we can see phi cap is the same as we got, so it will be phi cap. So v vector is omega s phi cap. So our surface current density will be sigma and omega cross s is omega s phi cap. So it is our answer in terms of s, and s is the distance from the center. Now we comes to the part B. So in this part the problem is as follows. A uniformly charged solid sphere of radius r and total charge q is centered at the origin and spinning at a constant angular velocity omega about the z-axis. Let's suppose it is rotating in anti-clockwise direction and its angular velocity is omega. So we know the basic definition of J, that is current density. J vector is equal to di upon dA perpendicular. Like part A, we can similarly find the formula of current density in terms of charge density and velocity. So we can write it as J vector is equal to rho V vector. Now our task is to find rho and V. So rho is simply Q upon 4 upon 3 pi r Q, because we have given that total charge is Q. V vector is omega vector cross r vector, and omega vector is omega z cap. You can find out the direction of omega by using right hand thumb rule. And r vector is r cap, and r is the magnitude of this vector. So if we write v vector is equal to omega z cap cross r cap, so v vector is equal to omega r z cap cross r cap. To find the z cap cross r cap, what we did in part A, we will do same in part B, but in part A we were having a cylindrical coordinate system, but in part B we will have spherical coordinate system. So in spherical coordinate system, the matrix is as follows: r cap, theta cap and phi cap is equal to sin theta, cos phi, sin theta, sin phi, cos theta, cos theta, cos phi, cos theta, sin phi minus sin theta, minus sin phi, cos phi and 0. And here is x cap, y cap, z cap. So from this matrix we can find z cross r cap. When we find z cap cross r cap, then after solving we will get z cap cross r cap is equal to cos phi y cap minus k sin phi x cap. And you can see from here, if you write phi cap is equal to and multiply these two matrices, then you will get phi cap is equal to minus sin phi x cap plus cos phi y cap. That is similar to here we got. So z cap cross r cap is equal to sin theta phi cap. So if we plug this value in this equation, then v vector is equal to omega r sin theta phi cap. So our current density will be rho, and we know the value of rho, omega r sin theta phi cap, and that is our answer. We found the current density in terms of r theta phi.